Massive stone circles and shimmering glass towers seem worlds apart, yet a silent conversation connects them across thousands of years. This is the story of the unspoken dialogue between ancient and modern builders, a tale hidden in stone, steel, and sacred geometry. You will learn how the deepest secrets of today's skyscrapers were first discovered by megalithic engineers. How did builders without computers achieve such impossible precision? Why do the same mathematical patterns appear in both pyramids and contemporary design? By the end, you will see every modern cityscape as a living library of ancient wisdom. What forgotten building principle from the past most surprises you? A Neolithic builder strains to set a massive stone into place, his hands reading the unyielding strength of the rock. Millennia later, a construction worker high above the city guides a steel beam, feeling its sleek potential through thick gloves. Though separated by ages, both are fluent in the same silent language, the fundamental grammar of structural integrity. The ancient builder understood stone's nature intuitively, how it resists being crushed, a property we call compressive strength. He knew a stone could bear immense weight if its load was directed straight down. This is why the great trilithons of Stonehenge stand firm, their massive lintels perfectly transferring force through their uprights. Modern engineering, in turn, has mastered steel's ability to resist being pulled apart, its incredible tensile strength. This allows for the slender, soaring frameworks of our skyscrapers, where steel cables and beams stretch and hold fast against wind and weight. This transition from stone to steel was not a rejection of ancient wisdom, but an evolution of means. The goal remained unchanged: to defy gravity and create something that endures. Look at the Parthenon, its marble columns precisely tapered to appear straight to the eye and to handle seismic forces with grace. Then observe the Eiffel Tower, an open lattice of iron that lets the wind pass through, a masterpiece of calculated lightness. One uses mass and compression, the other uses geometry and tension, yet both are brilliant answers to the same eternal question: how do we build to last? This deep, material conversation is the very foundation of the dialogue between the builders of old and the architects of now. That understanding of stone and steel reveals a deeper layer to this silent conversation, one written not just in materials but in mathematics. Long before blueprints or calculators, a master architect at a place like Stonehenge would have worked with simple ropes and wooden stakes. With these humble tools, they laid out perfect circles and precise alignments to capture the rising sun on the solstice. This was the practical application of sacred geometry, a system of mathematical ratios and proportions believed to mirror the fundamental order of the cosmos. These builders were using this language of numbers long before the term sacred geometry ever existed. We see this most famously in the Great Pyramid of Giza, where the ratio of its base to its height closely approximates the golden ratio, a special number often found in nature, from the spiral of a seashell to the arrangement of seeds in a sunflower. This same mathematical sequence, known as the Fibonacci sequence, appears in the layouts of temples from India to the Americas, but these principles were far more than just decoration. They represented a profound understanding of harmony and balance, principles that gave these structures an incredible physical stability while also imbuing them with deep spiritual meaning. The precise orientation of a Mayan temple to catch the first light of the solstice sunrise was not just a calendar. It was a statement that the temple itself was part of a larger cosmic machine. The columns of a Greek temple, with their subtle curves and perfect spacing, were designed according to these ratios to create a building that felt inherently right, harmonious, and eternally solid to the human eye and spirit. Mathematics served as the ultimate bridge, connecting the earthly act of construction to a cosmic understanding, creating spaces that physically and spiritually resonated with the universe's own patterns. This mathematical language of the cosmos did not vanish with the ancient world. It simply went quiet, waiting to be rediscovered. In the 20th century, the architect Le Corbusier developed a system he called the Modular, a scale of proportions based directly on the human form and the golden ratio. He was explicitly reviving those ancient proportional systems for the modern age. The very same mathematical relationships that guided the builders of the Egyptian pyramids now quietly shape the floor plans of our skyscrapers and the ergonomics of the products we use every day. Consider Frank Lloyd Wright's masterpiece, Falling Waiter. The house is a symphony of horizontal cantilevers and vertical stone, with its key dimensions and spatial relationships governed by the golden section. This is a design principle that would have felt completely familiar to a Renaissance architect studying the ruins of Rome, creating an immediate sense of harmony and balance for anyone who walks through it. On the other side of the world, the soaring shell structures of the Sydney Opera House are not random artistic gestures. Their forms are born from the same organic mathematics found in the segments of an orange or the unfolding petals of a flower. What these modern masters came to understand is that these are not arbitrary numbers. These timeless proportions create spaces that feel instinctively right to human perception. They resonate with a deep neurological wiring that connects us to patterns we have observed in nature for millennia. This is not mere nostalgia, it is a functional rediscovery. The ancient wisdom encoded in stone circles and temples continues to inform what we, on a fundamental level, find beautiful, harmonious, and truly human in our built environment. The same mathematical harmony found in modern design also underpins the most colossal engineering feats of the ancient world. Take the staggering platform at Baalbek in Lebanon, where 3 limestone blocks, each weighing close to 800 tons, form a foundation known as the trilithon. These are not merely stacked, they are fitted together with joints so impossibly tight that you cannot even slip a piece of paper between them. The question is not just how they moved these mountains of stone, but how they placed them with such breathtaking accuracy, long before the invention of the crane or the computer. Their methods were a symphony of applied physics. They understood leverage intimately, using long wooden beams and pivots to nudge weight that seems immovable. They likely constructed enormous earthen ramps, directing the flow of countless workers pulling on ropes in a coordinated effort that was itself a form of living mathematics. This was not brute force, it was brute intelligence. The principles they employed are the very bedrock of structural engineering today. The massive weight of each stone is distributed evenly across a wide base. The interlocking joints prevent shifting and dissipate energy. The entire structure was strategically positioned and shaped to withstand seismic activity, a testament to their deep understanding of how the Earth moves. These megaliths have endured for thousands of years, surviving earthquakes and harsh weather that would reduce many modern buildings to rubble. Their incredible longevity stands as a quiet, powerful challenge to our own culture of disposable construction. They ask us a simple, profound question. Why build for a century when you can build for millennia? That same audacious spirit that raised the megaliths now carves pathways through the very earth itself. The Channel Tunnel, a modern marvel stretching beneath the sea to connect England and France, finds its conceptual ancestor not in a building, but in the long, graceful arcs of ancient Roman aqueducts. These stone waterways conquered valleys and hills, defying geography to sustain entire cities. Both projects are monuments to the same human obsession, to draw a line where nature has drawn a barrier and to conquer distance through sheer engineering will. This drive to create livable space in the most hostile environments is another constant thread. High above the world, the International Space Station is a technological wonder, but in its core purpose, it is a direct descendant of the cliff dwellings at Mesa Verde, ingeniously carved into sheer rock faces for protection, or the vast, self-contained underground cities of Cappadocia. Each represents a profound adaptation, a creation of sanctuary where none should logically exist. Even the slender, gravity-defying lines of our greatest suspension bridges echo a much older technology. For centuries, the Inca people wove resilient bridges from mountain grass, spanning dizzying Andean canyons with structures that swung in the wind but held fast under load. The materials are now steel cable and carbon fiber, but the underlying principle of using flexible tension to conquer a vast, empty space is identical. Perhaps the most critical parallel lies in our response to a trembling Earth. Today's most advanced skyscrapers are engineered with complex damping systems to absorb the energy of earthquakes. Yet for over 1,000 years, multi-tiered Japanese pagodas have withstood countless violent tremors using a brilliant, intuitive form of seismic isolation. Their construction, featuring interlocking wooden joints that act like shock absorbers and a central pillar that sways independently of the structure, is a masterclass in dancing with the forces of nature rather than resisting them. These are not coincidences, they reveal a profound truth. Our tools have transformed beyond recognition, from stone hammers to computer models, but the fundamental challenges of building against gravity, wind, and earth remain. The silent dialogue continues not in the materials, but in the timeless human determination to find a way. That relentless human drive to build higher and wider has always been defined by a single, elegant problem: the quest for structural support. This journey begins with the most fundamental of systems, the post and lintel. Picture the massive upright stones of Stonehenge, with their equally massive horizontal slabs laid across the top. The principle is simple: two posts hold up a lintel, creating an opening below. But this method has a clear physical limit. The stone lintel can only span a certain distance before its own weight causes it to crack in the middle. To create larger, more open spaces, builders had to find a way to redirect the crushing force of gravity. The ancient Greeks refined the post and lintel to an art form, filling their temples with forests of closely spaced columns to support the heavy stone roofs above. It was the Romans who made the revolutionary leap with the arch. By arranging wedge-shaped stones in a semicircle, they discovered a way to channel weight not just downward, but outward along the curve of the arch, to be caught by supporting walls or other arches. This brilliant innovation allowed them to span vastly wider spaces, leading to monumental structures like the Pantheon, with its breathtaking, unsupported dome. For centuries, the arch and the dome represented the pinnacle of open interior space. Then, a new ambition arose in the Middle Ages: to build cathedrals that reached for the heavens, with walls so thin they seemed to be made of glass. This impossible dream was realized by the Gothic architects who invented the Flying Buttress. They essentially externalized the support system. These graceful stone arms reached out from the outside walls of the cathedral, catching the outward thrust from the tall, vaulted ceilings and channeling it down into the ground. This allowed the interior to become a skeleton of slender piers, with the walls between them filled with magnificent stained glass. The building's strength was no longer in its solid walls, but in its exoskeleton, a concept that would re-emerge millennia later. The next great revolution was the steel frame. With the ability to produce strong, consistent metal beams, architects could create a complete skeletal structure, a rigid grid of vertical columns and horizontal beams that carried all the building's weight. The outer walls were freed from their load-bearing duty, becoming mere curtains that hung from the frame. This is what made the modern skyscraper possible. Today, that evolution continues with even more efficient systems. The tube frame, where a dense network of exterior columns acts like a hollow reed to resist wind loads, and the diagrid, a lattice of diagonal beams that provides immense strength with far less material. Each of these leaps from the humble post and lintel to the soaring diagrid is not a rejection of the past but a refinement. Every generation of builders has stood on the shoulders of the last, looking at the same immutable laws of physics and asking the same timeless question: how can we build it stronger, higher, and more beautiful than ever before? The same quest for structural support is mirrored in our relentless search for better materials. The very first cities rose from the earth itself, built with sun-dried mud bricks in ancient Jericho. These humble blocks were a beginning, a simple agreement between human need and the raw elements. But then came the Romans, who transformed material science into an art. Their concrete was not just a mix of lime and volcanic ash. It was a kind of engineered stone, a material that could be poured into wooden forms to create structures of breathtaking scale and strength. The Pantheon's vast dome, a perfect hemisphere of Roman concrete, held the title of the world's largest unsupported concrete span for over 1,800 years. That is not just a record, it is a statement. Modern engineers still analyze samples of that ancient concrete, trying to decode the chemical secrets that gave it such incredible longevity, a durability that often surpasses our own modern mixes. This was not a lost art, it was a foundation. The Industrial Revolution then unleashed a new world of materials. Mass-produced steel and vast sheets of clear glass made entirely new forms of architecture possible. The Crystal Palace in London was a shock to the world, a building of unprecedented lightness and transparency, a greenhouse on a monumental scale that proved the potential of prefabricated parts. This new material reality directly enabled the skeletal steel frames of the first skyscrapers, transforming city skylines forever. Today, that evolutionary chain continues at an astonishing pace. We are developing concrete that can heal its own cracks with embedded bacteria, a literal return to organic principles. We have engineered ceramics like transparent aluminum, a material that seems like science fiction, offering the strength of metal with the clarity of glass. We weave carbon fiber composites into forms that are both incredibly strong and impossibly light. This is not a series of disconnected inventions. It is a continuous, unbroken conversation of experimentation and improvement. Each generation of builders inherits the material wisdom of the last, tests its limits, and adds a new chapter, forever standing on the shoulders of the giants who came before. The same celestial precision that guided ancient builders still whispers from the stones. 5,000 years ago, an architect in Ireland designed the passage tomb of Newgrange with a single, brilliant purpose. On the winter solstice, as the sun crests the horizon, a narrow beam of sunlight pierces the darkness, traveling down a long, narrow passage to flood the inner chamber with golden light for just 17 minutes. This was not an accident. It was a meticulously calculated event, an act of architecture designed to capture a moment of cosmic alignment, repeated every year for millennia. This profound connection to the heavens is a global phenomenon. In the American Southwest at Choco Canyon, a sliver of sunlight, a sun dagger, slices across a spiral petroglyph on a cliff face, marking the solstices and equinoxes with stunning accuracy. The Great Pyramid of Giza is aligned to the four cardinal directions with a margin of error smaller than 1/15 of a single degree. To achieve this, its builders needed more than simple tools. They possessed a deep, generational knowledge of the night sky, tracking the slow precession of stars and the cyclical paths of the sun and moon over lifetimes. These structures were far more than tombs or temples. They were colossal stone calendars, cosmic clocks that anchored human ritual to the immutable rhythms of the universe. They connected the community below to the powers above, turning abstract celestial events into tangible, predictable experiences of light and shadow within a sacred space. This required a sophisticated understanding of geometry and observational astronomy that we are only beginning to fully comprehend. The enduring power of these places lies in this dual nature. They are simultaneously grounded in the earth and reaching for the stars, creating architecture that makes us feel both profoundly placed in our world and intimately connected to the cosmos beyond. That profound celestial connection was never truly lost. It has simply been reborn in the language of modern science and sustainability. We may no longer build temples aligned to solstices for purely spiritual reasons, but the principles of cosmic alignment are more critical than ever. Today's architects engage with the sun's path not to mark a sacred day, but to capture its energy and light with breathtaking efficiency. This is passive solar design, a method where a building's orientation, its windows, and its materials are all strategically chosen to work with the sun's daily and seasonal movements. A south-facing wall of thermal mass, like concrete or stone, will absorb the sun's low winter warmth during the day and slowly release it through the cool night. In the summer, a simple overhang can block the high, harsh midday sun, keeping the interior naturally cool. This is not new technology. It is a high-tech rediscovery of what ancient builders from the ancestral Pueblones to the Chinese masters of Feng Shui understood intuitively, that the most intelligent building is one that works in concert with its environment. This dialogue with natural forces extends to the wind. Look at the Bahrain World Trade Center, a pair of soaring towers with 3 massive wind turbines suspended between them. The towers themselves are sculpted to funnel the prevailing coastal winds directly into the turbines, generating a significant portion of the building's own power. This brilliant design finds its direct ancestor in the ancient Persian wind catchers, those tall, clever towers that captured breezes and channeled them down to cool buildings and storehouses in the desert. The principle is identical: to harness an invisible, flowing force of nature as a fundamental part of the architecture. We see this same full-circle moment in our most extreme future projects, the plans for habitats on the Moon or Mars. These structures will have to be sealed environments, protecting their inhabitants from radiation, extreme temperatures, and a complete lack of atmosphere. In many ways, they are the ultimate descendants of the cliff dwellings at Mesa Verde or the underground cities of Cappadocia, creating a safe, self-contained bubble of life within a profoundly hostile landscape. The challenges are monumental, but the core philosophy is ancient: build using the local resources and create a sanctuary against the elements. This is the beautiful, silent convergence happening right now. The most advanced sustainable architecture on our planet is not just looking forward, it is looking back, rediscovering a timeless truth that the ancients carved in stone. True innovation is not about conquering nature, but about listening to it, learning its rhythms, and once again, building in harmony with the cosmos. The silent conversation between ancient and modern builders flows most literally through water. 5,000 years ago, the city of Mohenjo-Daro thrived in the Indus Valley with a municipal water system that would impress any modern engineer. Its streets were lined with covered drains, its homes featured indoor baths, and a sophisticated network of wells and channels managed both fresh water and waste with stunning efficiency. They understood the principles of sanitation and urban hydrology on a scale that would not be seen again for millennia. Half a world away, the Nabateans carved their magnificent city of Petra from rose-red cliffs in a desert that received only a few inches of rain each year. Their survival depended on an ingenious and beautiful system. They sculpted the entire landscape into a vast catchment area, with channels and dams that captured every precious drop of flash flood rainwater, funneling it through carved conduits into massive, hidden cisterns. This was not just plumbing, it was a sacred economy of water, a life-giving system built on an intimate understanding of a harsh environment. Then came the Romans, who turned water engineering into an imperial art form. Their aqueducts marched across valleys and through mountains, using gravity alone to transport millions of gallons of fresh water daily over distances of 50 miles or more. The precise, gentle slope required to maintain this flow, often just a few inches of drop per 100 feet of channel, stands as a monument to their surveying skill. They were masters of moving water on a colossal scale, feeding public baths, fountains, and the homes of an entire metropolis. For centuries, modern cities turned away from this wisdom. We buried rivers in concrete pipes, paved over wetlands, and tried to force water to obey our commands. But now, as water scarcity becomes a critical global challenge, we are relearning the old ways. Today's green infrastructure embraces what the Nabateans and the builders of Mohenjo-Daro knew instinctively. We install permeable pavements that allow rainwater to seep back into the earth, replenishing aquifers instead of overwhelming sewers. We construct rain gardens and bioswales, which are carefully designed landscape features that use soil and plants to naturally filter pollutants from stormwater before it reaches our rivers. We are rediscovering the ancient logic of harvesting rainwater from our roofs, just as desert cultures have done for thousands of years. The most advanced urban planning today does not fight the water cycle. It collaborates with it, creating sponge-like cities that absorb, clean, and reuse water in a continuous, sustainable loop. This is not a step backward. It is the silent dialogue in its most vital form, a return to the profound understanding that to build a lasting civilization, you must first learn to listen to the flow of water. That mastery of water in ancient cities points toward an even grander achievement, the planned city itself. The streets of Mohenjo-Daro, laid out over 4,000 years ago, were not a tangled web of accidental paths. They formed a precise grid with main avenues and smaller lanes dividing the city into orderly blocks. This was not just about neatness, it was a system for efficient movement, sanitation, and social order, a level of urban planning that would not be rivaled for centuries. Now look down from the sky upon the island of Manhattan. Its own rigid grid, imposed in the early 19th century, is a direct echo of that same organizational impulse, a solution to the chaotic growth of a modern metropolis. Both cities, separated by millennia, answered the same fundamental needs, creating frameworks for movement, defining public and private spaces, and embedding infrastructure into their very bones. The Romans perfected this concept with their military camps, which grew into great cities. They established the Cardo and the Decumanus, the two main streets that crossed at the city center, creating a clear north-south and east-west axis. This pattern provided an immediate sense of orientation and order, a template for urban life that you can still trace in the street plans of countless European towns today. But then, a different model emerged. Medieval cities grew not from a central plan but organically, winding around hills, rivers, and ancient footpaths. Their narrow, crooked streets might seem like chaos compared to a Roman grid, but they created intimate, human-scale environments. A person walking through a medieval town experienced a constantly shifting vista with surprises around every corner, fostering a deep sense of place and community. For a long time, modern planning saw this organic growth as inefficient, something to be paved over with straight lines. But now, a powerful movement in urban design is looking back to these ancient models for answers to our own urban problems. The principles of new urbanism actively champion the very features that made ancient cities so livable. They advocate for mixed-use districts where homes, shops, and workplaces coexist within a short walk, just as they did in a Roman neighborhood or a medieval quarter. They push for abundant, accessible public spaces, from the agoras of ancient Greece to the piazzas of Renaissance Italy, understanding that these are the vital hearts of community life. They are reviving the narrow, walkable streets that prioritize people over cars, rediscovering the human scale that medieval builders understood intuitively. The dialogue between ancient and modern urban design is revealing a profound truth. The most successful human habitats, whether carved from stone or forged from steel and glass, seem to follow a set of timeless principles. They balance order with variety, efficiency with beauty, and private life with vibrant public gathering. They remind us that a city is not just a collection of buildings, but a living, breathing organism, and its health has always depended on this ancient, silent wisdom. This silent dialogue echoes not only in stone and steel, but in the very moment a building is born. Before a single stone was laid for a Mesopotamian ziggurat, a profound ritual took place. The builders would carve a detailed inscription onto a clay tablet, often listing the king who commissioned the structure and the gods to whom it was dedicated. This tablet, along with precious objects like beads or amulets, was carefully placed in a foundation box and buried beneath the cornerstone. This was not a mere formality. It was a sacred act, a ritual deposit intended to eternally connect the physical building to the divine, securing the blessings of the gods and sending a message of legacy to any who might uncover it in the distant future. This powerful impulse was a global phenomenon. The Romans practiced a nearly identical tradition, consecrating their temples and aqueducts with sacrifices and offerings to ensure their permanence. In ancient China, the meticulous art of feng shui governed the placement of every foundation, aligning the structure with the cosmic flow of energy for harmony and prosperity. Across the ocean, Maya kings would dedicate their towering pyramids with ceremonies that involved precious jade and even ritual bloodletting, binding the fate of the kingdom to the fate of the stone. In every case, construction was more than a technical process. It was a spiritual undertaking, a collaborative venture between the human and the divine to create something that would truly endure. While today's groundbreaking ceremonies have largely shed their overtly religious nature, the symbolic core remains startlingly intact. We still gather for cornerstone layings, embedding sealed containers filled with coins, newspapers, and messages for the future. We mount commemorative plaques that declare who built this place and why, a direct descendant of those Mesopotamian foundation tablets. We inter time capsules, hoping that someone, centuries from now, will unearth our story. This enduring practice reveals a profound psychological truth about humanity. We feel a deep need to mark our most significant constructions as meaningful endeavors, to imbue our steel and concrete with purpose that transcends their mere function. The technology has changed beyond recognition, but the human heart behind the ritual has not. We are still building connections not just to gods, but to the generations who will follow us. A skyscraper is not just an office building. A bridge is not just a way across a river. They are our own foundation deposits, our statements of value, our aspirations cast in permanent form. continuing a conversation with the future that began thousands of years ago. The stones of Chartres Cathedral do more than simply reach for the heavens. They pull your gaze upward along the ribbed vaults and through the kaleidoscope of stained glass until you feel a profound sense of awe, a quieting of the self in the face of something immense and transcendent. This was not a happy accident. The master builders knew exactly what they were doing, using sheer scale, the manipulation of light, and sacred geometry to orchestrate a very specific emotional and spiritual experience. They designed for the human soul. Walk from that ancient nave into the vast, sun-drenched atrium of a modern airport terminal, and you might feel a surprising echo of that same sensation. The space is designed to feel open, efficient, and liberating, to ease the stress of travel and inspire a sense of movement and possibility. The psychological power of architecture is a tool as old as building itself. Ancient Egyptian pharaohs used overwhelming scale and endless, repeating colonnades in their temples to intimidate visitors and reinforce their divine authority. In contrast, a Japanese Zen garden, with its carefully raked gravel and strategically placed stones, is engineered for a completely different state of mind, one of quiet contemplation and inner focus. These builders worked from an intuitive, centuries-old understanding of how form and space shape human feeling. Today, we have a new field called evidence-based design that puts this ancient intuition under the microscope. Rigorous scientific studies now confirm what the builders of Chartres knew in their bones. They show that the height of a ceiling can directly influence how we think. High, voluminous ceilings promote abstract thinking and creative, expansive ideas, while lower, cozier ceilings help us focus on fine details and concrete tasks. They quantify how exposure to natural light in a workplace or hospital room can significantly improve mood, reduce stress, and even speed up patient recovery times. The arrangement of spaces themselves, whether encouraging chance encounters in an open office layout or providing private nooks for concentration, directly shapes our social interactions and sense of community. This scientific exploration has blossomed into the field of neuroarchitecture, which uses advanced brain imaging to study how different environments actually affect our brain function and physiology. We can now see the neural pathways that light up when we enter a space we find beautiful or calming. We can measure the stress hormones that drop when we are in a room with a view of nature. This is not replacing the ancient wisdom. It is validating it with hard data, adding a layer of scientific precision to that timeless, intuitive understanding. The silent dialogue continues, but now we are listening to it with brain scanners as well as our hearts, proving that the most profound function of any structure, from a stone circle to a steel-framed hospital, is its impact on the human experience inside it. The silent dialogue between builders echoes not only in stone and light, but in the very air we hear. High on the stepped pyramids of the ancient Maya, a single clap can transform into the sharp, chirping cry of the Quetzal bird. This was no accident of stone. It was a carefully engineered phenomenon, a sacred echo designed to bridge the human and the divine, turning a simple sound into a spiritual message. Half a world away, inside the dome of St. Paul's Cathedral, a whisper spoken against one wall can travel with impossible clarity along the curve of the stone to be heard perfectly on the opposite side. This whispering gallery is a masterpiece of acoustic manipulation, a secret channel for sound that feels like magic but is pure, calculated physics. These ancient and medieval builders possessed a deep, intuitive understanding of how sound waves behave, shaping their stone to guide, amplify, and transform the human voice and other sounds. They were the world's first acoustic engineers, working through generations of observation and refinement. The grand open-air theaters of Greece and Rome stand as the ultimate testament to this lost science. Carved into hillsides, their semicircular banks of stone seats acted as a giant sound filter, trapping and clarifying the voices of actors on the stage. The precise shaping of the stage floor and the strategic placement of architectural elements helped project words with stunning clarity to every one of the thousands of spectators, all without a single microphone. This was not a vague hope for good acoustics. It was a precise and repeatable architectural technology. That ancient pursuit of perfect sound has never truly ended. It has simply evolved. The world's great modern concert halls, like the Berlin Philharmonic, are the direct heirs to those Greek theaters. Their architects and engineers spend years designing every surface, every angle, every material to achieve the perfect reverberation time, the ideal clarity, and the most enveloping sonic experience. They use complex computer models to simulate sound waves, but they are solving the same fundamental problem. They are crafting space to serve sound. Whether in an ancient temple, a medieval cathedral, or a state-of-the-art opera house, the goal remains identical. How do you make a whisper carry? How do you make a chant resonate with cosmic power, or a symphony feel as intimate as a private performance? The materials have changed from limestone to composites, and the tools from simple observation to digital simulation, but the conversation across the centuries is unmistakable. The quest to shape air itself with stone and steel continues, proving that the most profound dialogues are often the ones we can hear. That same acoustic brilliance finds a parallel in the mastery of climate. High on the sun-baked cliffs of Mesa Verde, the ancestral Pueblones built dwellings tucked deep into south-facing alcoves. In the summer, the high arc of the sun left the rooms in cool shadow. When winter came, the sun hung low, its rays penetrating deep into the dwellings to warm the massive stone walls. These walls acted as a thermal battery, absorbing heat by day and releasing it slowly through the cold desert night. This is not a forgotten secret. It is the exact same principle of thermal mass and solar orientation that defines today's most rigorous passive house standards, where buildings are engineered to maintain a comfortable temperature with minimal energy input. The ancient Persians faced a different challenge, the scorching, still air of the desert. Their answer was the wind catcher, a tall, clever tower that captured even the faintest breeze high above the ground. This captured air was then channeled down into the heart of the building, often passing over a pool of water to be cooled by evaporation before flowing through the living spaces. It was a form of natural air conditioning that required no electricity, only a profound understanding of airflow and physics. Even the Romans understood the luxury of climate control. In their villas and public baths, they built hypocaust systems where a furnace-heated air would circulate in the empty space beneath raised tile floors, warming the entire room from the ground up. If that sounds familiar, it should. The principle is identical to the radiant floor heating systems being installed in modern, sustainable homes today. These were not primitive solutions. They were highly sophisticated adaptations, born from centuries of observing and cooperating with local environments. Now, as we confront global energy and environmental crises, contemporary architects are turning back to this deep well of vernacular wisdom. They are not simply copying old designs. They are engaging in a fruitful dialogue, merging ancient, time-tested principles with cutting-edge technology. A modern building might use computerized models to optimize the shape of a wind-catching facade, or employ phase-change materials that mimic the thermal storage capacity of ancient stone walls with far less weight. This is not a rejection of progress. It is a recognition that the oldest forms of intelligence, those born from necessity and a deep connection to place, hold some of the most powerful keys to our future. The silent dialogue between builders has become an urgent global conversation, one where traditional wisdom and modern innovation are joining forces in a shared mission of planetary stewardship. A modern construction site begins with a bulldozer, its blade reshaping the very earth to create a flat, uniform platform for a new structure. This approach asserts human will upon the landscape, a testament to our power to remake the world to our specifications. Now journey to the Andes and stand among the ruins of Machu Picchu. Here, the Incan builders asked a different question of the mountain. Instead of leveling the peak, they listened to its form. Terraces cascade down the slopes following the natural contours. Structures are fitted between granite outcrops, their walls curving to embrace the living rock. The entire city feels not built upon the mountain, but woven into its very fabric, a collaboration between human intention and geological reality. This philosophy of integration was a global constant. In traditional Japanese architecture, the principle of shake, or borrowed scenery, was fundamental. A garden or a home was not designed as a closed world, but as a frame that deliberately incorporated distant mountains, a grove of trees, or the course of a stream into its composition. The view was not an accident. It was an architectural material as important as wood or paper, seamlessly blending the man-made and the natural into a single, harmonious experience. Countless indigenous building traditions hold this same core belief, that construction is a form of dialogue with the land, a respectful partnership rather than a declaration of conquest. Today, this ancient sensibility is re-emerging with profound urgency under the banner of biophilic design. Contemporary architects are once again learning to work with the topography, not against it. They design foundations that step gently down a hillside, preserving the mature trees that have stood for generations. They create living walls that breathe and roofs that bloom, blurring the line between building and ecosystem. This is far more than an aesthetic choice. It is a fundamental shift in perspective, a return to that older, wiser understanding that we are not separate from nature, but a part of its intricate system. The silent dialogue is reaching its most critical chapter, reminding us that the most advanced and sustainable buildings may not be those that dominate the skyline, but those that know how to listen to the ground beneath them. That profound continuity between ancient intuition and modern science is written in the unchangeable language of mathematics. This is the universal builder's tongue, a dialect of numbers and shapes that transcends culture and millennium. Long before Pythagoras formalized his theorem, Egyptian rope stretchers, known as harpodonapti, were using its principle to lay out perfect right angles for the foundations of their pyramids and temples. They would take a long rope with 12 equally spaced knots, forming 13 segments. By staking out a triangle with sides of 3, 4, and 5 segments, they guaranteed a perfectly square corner every single time. The same immutable rule of 3 squared plus 4 squared equals 5 squared that guided them is now embedded in the software that calculates the steel connections of a skyscraper. This is not a coincidence, it is evidence of a shared reality. The soaring vaults of a Gothic cathedral with their intricate stone lacework were only possible because the master masons possessed a deep, practical knowledge of geometry. They knew how to calculate the complex thrusts and counter-thrusts, using compass and straightedge to translate celestial ambition into stable stone. Today, computer-aided design programs perform nearly identical calculations in milliseconds, running finite element analysis to determine how wind will flow around a building or how weight will distribute across a cantilever. The tool has evolved from a physical compass to a digital algorithm, but the underlying geometric truth being applied is precisely the same. This mathematical consistency even governs the very units we build with. The ancient Romans used a standard brick dimension and a modular system of measurement that allowed for the rapid construction of their empire. Today, we have dimensional lumber with its 2x4s and 4x8 sheets of plywood, creating a universal language for modern carpentry that streamlines construction across the globe. This modular thinking reaches its most beautiful expression in the fractal patterns found in traditional African architecture. The recursive, self-similar geometry of a compound's layout, where the same branching pattern repeats from the main gate down to the smallest sleeping hut, mirrors the organic logic of a snowflake or a fern. Now, architects use parametric design algorithms to generate buildings that look grown rather than built, with facades and structures that mimic these same fractal patterns for both aesthetic beauty and structural efficiency. The silent dialogue across time is not just about shared challenges, it is a shared discovery. Each generation of builders, from the rope stretcher to the software engineer, is independently accessing the same eternal mathematical truths that govern stability, function, and beauty in our universe. The language was always there, waiting in the stones and the stars for anyone with the wisdom to listen. The stones of Machu Picchu or the steel of a skyscraper are only half the story. The true monument is always the human organization behind it. Consider the sheer human force required to build the Great Wall of China. This was not a single project but a continuous campaign stretching across dynasties for more than 2,000 years. Millions of laborers, soldiers, and convicts were mobilized, moving across vast and unforgiving terrain. The administration needed to manage this ocean of people was staggering. They required systems for recruitment, for supply lines that stretched for hundreds of miles, for communication between distant outposts, and for housing and feeding this immense, moving population. This was not brute force. It was a bureaucracy of epic scale, a managerial feat that rivals the coordination of any modern megaproject, from a transcontinental railway to an international space station. The ancient Egyptians faced a similar challenge on a more concentrated site. The pyramid builders of Giza were not slaves in chains, as popular myth suggests, but a highly organized workforce of tens of thousands of skilled laborers. Archaeological evidence reveals purpose-built workers' villages with bakeries producing thousands of loaves of bread, breweries making beer, and facilities for drying fish on an industrial scale. This was a sophisticated, state-run logistics operation designed to sustain a specialized society of quarrymen, haulers, stonemasons, and engineers for generations. The greatest obstacle they overcame was not the weight of the stones, but the monumental task of housing, feeding, and coordinating the human energy required to move them. This reveals a profound truth. The ultimate challenge of monumental construction has never been purely technical. It has always been, first and foremost, a challenge of human organization. Modern project management, with its intricate Gantt charts mapping every task and its critical path methods identifying potential delays, is the direct intellectual descendant of those ancient administrative innovations. Today's supply chain coordinators, who ensure that steel beams arrive at a construction site just as the foundation is finished, are performing the same essential function as the Egyptian officials managing the flow of limestone from Tura and granite from Aswan. This social dimension of building connects eras in a complex and often uncomfortable continuum. It is the story of mobilizing collective effort toward a shared architectural goal, a thread that runs from the corvée labor of ancient empires through the guilds of medieval cathedrals to the unionized workforces of today. The methods of motivation and compensation have transformed, but the fundamental reality remains. Every great structure that touches the sky is at its heart a testament to our ability to organize ourselves on a breathtaking scale. Venice is a city that floats on a forest. Its magnificent palazzos and piazzas do not rest upon solid ground, but on a dense grid of wooden piles, driven deep into the shifting mud and silt of the lagoon. For centuries, this was the only way to anchor a metropolis in such unstable terrain, a brilliant, patient response to an impossible building site. Today, engineers face a similar challenge in earthquake zones, where the ground does not sink but shakes with violent force. Their solution of base isolation is a high-tech echo of that Venetian ingenuity. Instead of trying to rigidly resist the tremors, they install massive rubber and steel bearings between the building and its foundation. These isolators act like shock absorbers, allowing the ground to shudder while the structure above sways gently and safely. The principle is the same, to create a flexible buffer between a volatile earth and the need for human stability. This dialogue with water and earth extends to the threat of floods. The traditional stilt houses of Southeast Asia have stood above monsoon-swollen rivers for generations, their elevated floors allowing water to pass harmlessly beneath. This ancient, common-sense design is being reborn in amphibious architecture. In places like the Netherlands, entire communities are being built with homes that rest on hollow foundations. During a flood, these foundations fill with water, causing the entire house to float up like a boat, guided by vertical posts that keep it from drifting away. When the waters recede, the house settles gently back onto its foundation. This is not a rejection of the old way, but a refinement of it, using modern buoyant materials to achieve the same life-preserving goal. For millennia, builders in scorching deserts have used wind towers and thick, insulating walls to create cool oases. In hurricane-prone regions, traditional circular or hexagonal building forms have proven naturally more resilient to high winds than rectangular boxes. These are not primitive designs, they are time-tested adaptations, a deep historical repository of strategies for survival. As our own climate becomes more volatile, this repository is no longer just a curiosity. It is one of our most valuable resources, a silent conversation with the past that holds urgent wisdom for building a resilient future. A master mason would press his personal symbol into a block of stone destined for the soaring vault of a cathedral. This mark was more than a signature, it was a promise of quality and a direct line of accountability stretching back through the entire building process. In an age before formal blueprints, knowledge was not stored on paper but in the minds and hands of the craftsmen. The master builder held the grand vision, a three-dimensional understanding of the structure passed down through a long and secretive apprenticeship. He would guide his workers with simple, full-scale templates carved from wood and with lines scratched directly onto the floor of the tracing house, a dedicated room where the geometry of the entire building was laid out. These sacred techniques were guarded within the closed circles of the Mason guilds, a living library of practical engineering that was transmitted from one generation to the next through demonstration, ritual, and memory. This was a chain of wisdom that could not be easily broken, ensuring that the secrets of how to make stone defy gravity were preserved for centuries. The Renaissance shattered this closed system with the invention of the printing press. Suddenly, architectural knowledge could be captured and disseminated. Visionaries like Leon Battista Alberti and Andrea Palladio published detailed treatises, complete with precise drawings and mathematical explanations of classical proportions. These books democratized design, allowing a builder in England to construct a villa based on principles observed in the ruins of ancient Rome. The drawing itself evolved from a rough sketch into an instrument of control, a two-dimensional representation that attempted to capture a three-dimensional reality. Yet a flat drawing, no matter how detailed, can never fully convey the spatial complexity of a building or the intricate sequence of its assembly. This fundamental gap between the idea and the physical object drove the next great leap. We moved from hand-drafted lines to computer-aided design, and now to building information modeling, or BIM. This is not just a digital drawing. It is a dynamic, intelligent database that constructs the entire building virtually before a single shovel hits the dirt. Every beam, pipe, and wire is modeled in 3 dimensions, complete with data on its cost, manufacturer, and installation schedule. It allows architects, engineers, and contractors to collaborate in a shared digital space, identifying conflicts between, say, a structural beam and an air conditioning duct long before they become costly errors on the construction site. This evolution from the mason's mark to the digital twin is all part of the same endless quest. How do we perfectly translate the magnificent vision in one person's mind into a physical, enduring reality? It is the ultimate challenge of communication, a silent dialogue not between builders, but between imagination and the unyielding nature of stone and steel. An Egyptian temple did not welcome you, it overwhelmed you. Its towering columns and colossal statues were designed to make any visitor feel insignificant, a mere mortal standing before the divine power of the pharaoh. This was architecture as psychological warfare, using sheer, crushing scale to communicate absolute authority. Yet walk into the concentric seating of an ancient Greek theater, and you encounter a completely different philosophy. Here, the design is a masterclass in connection. Every seat, from the front row to the very last, was carefully calculated to maintain a clear sightline to the stage and an acoustic link to the actor's voice. The architecture fostered a shared, communal experience, uniting the crowd in a single, human-scaled moment. This fundamental tension between the building that dominates the individual and the one that serves the community is a conflict as old as architecture itself. The sprawling, egalitarian layout of a Neolithic village, with its roundhouses of similar size, spoke of a communal ethos. In stark contrast, the rigid, axial symmetry of a Roman forum, culminating in a grand temple, was a physical map of imperial order and hierarchy. The scale of our buildings has always been a direct reflection of our cultural priorities. Today, that same negotiation plays out in our city centers. The gleaming skyscraper is a modern ziggurat, its breathtaking height a clear symbol of corporate ambition and economic power. It is meant to impress, to inspire awe, and to dominate the skyline. Yet within those same cities, a powerful movement toward human-centered design seeks to pull the focus back to the individual. This philosophy prioritizes walkable streets, accessible public plazas with places to sit and rest, and buildings that feel inviting rather than intimidating. It asks how a space feels to a child, to an elderly person, or to someone with a physical disability. The greatest challenge for a modern architect is to balance these two impulses, to create a structure that possesses a monumental presence without sacrificing humane proportions. How do you design a library that feels both grand and intimate? How do you craft an airport terminal that conveys the awe of travel without making the traveler feel lost and anonymous? This eternal architectural conversation is about more than just aesthetics or engineering. It is a profound dialogue about who we are, what we value, and how we choose to position ourselves in the delicate space between our individual experience and our collective, soaring aspirations. An Egyptian tomb painter worked in total darkness until the appointed hour when a single shaft of sunlight would pierce the interior, illuminating his divine subject for just a few precious minutes. This was light with intention, a tool as deliberate as any chisel. For the architects of the ancient world, sunlight was not merely something to be let in. It was a material to be quarried, shaped, and directed. They designed entire structures as intricate machines for harvesting and sculpting illumination. In the depths of the Great Pyramid, narrow shafts align with celestial bodies, not for ventilation, but to channel starlight directly to the pharaoh's eternal chamber, forging a literal connection between the king and the cosmos. This mastery of light reached its most breathtaking expression in the Gothic cathedral. Here, stone was made to disappear, replaced by vast expanses of colored glass that transformed raw sunlight into a medium of sacred storytelling. A peasant who could not read a single word could stand in that kaleidoscopic glow and understand the entire narrative of their faith, written in rubies, sapphires, and emeralds of light. The building itself became a lens, focusing divine revelation into a visceral, emotional experience for every person who entered. The Romans approached light with equal drama but different means. The oculus at the crown of the Pantheon's dome captures a brilliant, moving spotlight that travels across the marble floor throughout the day, marking the passage of time with celestial precision. It is a sundial on a monumental scale, a constant reminder of the sun's dominion. Meanwhile, in Islamic architecture, the problem was the sun's intense glare. The solution was the mashrabiyah, those exquisitely carved wooden screens that fractured the harsh desert light into 1,000 tiny, dappled patterns. They created a soft, diffused glow that provided privacy and cooling while turning ordinary sunlight into a constantly shifting work of art. This ancient recognition of light's power never faded. The modern architect Louis Kahn spoke of designing rooms of light, not just spaces. He understood that a room without natural light is not a room at all. In his Kimbell Art Museum, he created long, curved vaults with a narrow slit at the apex. Below this slit, a perforated aluminum reflector hangs, capturing the sun's rays and scattering them into a soft, silvery luminescence that bathes the artworks below. It is a deeply modern system, yet its goal is ancient, to make the building itself a source of sublime, controlled daylight. Today, this dialogue continues in light wells that pull illumination deep into a building's core, in clerestory windows that wash vaulted ceilings with ambient glow, and in computer-modeled facades that direct sunlight to maximize warmth in winter and shade in summer. The methods have evolved from stone shafts to parametric algorithms, but the silent conversation remains. How do we harness the sun not just to see, but to feel? How do we build not with light, but from it? The ziggurats of Mesopotamia did more than scrape the sky. They physically lifted the priest-king above the common world, a man-made mountain placing him closer to the gods he claimed to represent. This was architecture as a direct assertion of divine right, a permanent, towering argument for a ruler's legitimacy. Across the Mediterranean, the Romans perfected a different kind of statement. Their triumphal arches were not homes for gods but permanent advertisements for military victory. Carved with scenes of conquest and submission, these stone monuments transformed a single day's parade into an eternal reminder of who held power and who had been defeated. This impulse to build big as a demonstration of authority is a universal constant. The sprawling Forbidden City in Beijing was meticulously designed according to cosmic principles, but its endless courtyards and towering gates served a very earthly purpose: to overwhelm any visitor with the unimaginable scale of the emperor's power. Every step deeper into the complex reinforced the social chasm between the ruler and the ruled. The palace at Versailles served a similar master. King Louis XIV used its extravagant scale and opulent gardens not just for pleasure, but as a gilded cage for his nobility, keeping potential rivals close, indebted, and under his constant watch. The architecture itself became a tool of political control. This language of power did not fade with the Age of Kings. It simply found new patrons. Walk through the heart of any major capital today, and you will see the same principles carved in granite and glass. Government buildings are almost universally designed with massive columns, grand staircases, and imposing facades. These are not merely aesthetic choices, they are deliberate signals of stability, tradition, and unassailable authority. They are meant to make an individual feel small, to communicate that the institution is permanent and you are temporary. The modern corporate headquarters follows the same ancient playbook. The sleek, towering skyscraper bearing a company's name is the contemporary ziggurat. Its incredible height is a declaration of economic dominance, its reflective glass skin projecting an image of impenetrable efficiency and cool control. The materials themselves speak volumes: the cold weight of marble, the shimmering expense of bronze, the engineered perfection of steel, all selected to project an image of unshakable permanence and wealth. This architecture has a profound psychological impact. The long, echoing corridor leading to a powerful executive's office is designed to build anticipation and anxiety. The elevated desk, the oversized chair, the deliberate arrangement of seating, these are all subtle tools that reinforce hierarchy before a single word is spoken. From the throne room of an ancient palace to the boardroom of a multinational corporation, the spatial dynamics are eerily similar. They are engineered to remind you of your place within a carefully constructed social order. So the next time you stand before a monumental building, ask yourself not just how it was built, but why it was built that way. What silent message is it sending about power, control, and your role in the world it governs? A perfect structure is a completed lesson, but a flawed one is often the greatest teacher. The Leaning Tower of Pisa was a near disaster from the start, its famous tilt beginning when builders reached only the third story. The soft, unstable subsoil of clay, fine sand, and shells simply could not support the weight. This was not a failure of ambition, but of foundation engineering. For centuries, the tower was a monument to a miscalculation, slowly sinking and threatening to topple entirely. Yet this very flaw forced generations of engineers to confront the problem, leading to ingenious stabilization efforts that have ensured its survival. The tower's enduring, precarious beauty is a permanent reminder that the ground beneath our feet is the first and most critical collaborator in any construction. The Romans faced a similar, more tragic lesson in the year 27, when a wooden amphitheater in the town of Fidene, packed with spectators, collapsed. The historian Tacitus recorded that tens of thousands were killed or injured. The Senate's investigation revealed that the foundation was inadequate and the wooden superstructure was shoddily built for profit. In response, Rome enacted some of the world's first known building codes, mandating that all future amphitheaters be built on solid foundations and requiring their approval by officials. A catastrophe became a catalyst for regulation, embedding the hard-won knowledge of failure directly into the law of the land. This pattern repeats throughout architectural history. When the vaults of early Gothic cathedrals showed signs of cracking under their own weight, the Flying Buttress was not just invented, it was perfected. It was a direct, elegant solution born from observing structural weakness. The great earthquake that struck Lisbon in 1755 did not just level a city, it leveled old assumptions. The subsequent reconstruction became a massive laboratory for seismic-resistant design, pioneering the use of a flexible wooden cage framework known as gaiola pombolina that could sway with the tremors. Each of these failures, from a leaning campanile to a collapsed arena, forced a leap in understanding. They created an accumulating library of what not to do, a body of knowledge written in rubble and reinforced by loss. Today, the field of forensic engineering dedicates itself to this exact dialogue with the past. When a modern building or bridge fails, teams of experts descend to piece together the physical evidence, much like archaeologists sifting through the ruins of a collapsed Roman structure. They are asking the same fundamental questions. Where did the stresses concentrate? Which material gave way first? Was the design flawed, or was the execution poor? The answers they find do not just assign blame, they become data points that refine our computer models and update our safety codes. This relentless, iterative process of trial, error, and improvement is perhaps the most vital and practical aspect of the silent conversation. It is a humbling acknowledgement that every generation of builders stands not only on the shoulders of past genius, but also on the solid ground of past mistakes. The future of this architectural dialogue is already rising from the ground, not carved by hand but printed layer by layer. We are entering an era where entire buildings can be extruded from giant nozzles, where smart materials can sense stress and repair their own cracks, and where we are planning habitats for the dust-filled plains of Mars. Yet even here, in our most forward-looking visions, the conversation with the ancient builders continues in profound and surprising ways. One of the most powerful new languages in this dialogue is biomimicry, the conscious imitation of nature's genius. We are once again observing the natural world, just as the earliest builders studied the strength of a bird's nest or the stability of a honeycomb. The Eastgate Center in Zimbabwe is a stunning example. Its ventilation system was inspired by the intricate, self-cooling mounds of African termites. Without conventional air conditioning, the building uses dramatically less energy, its form and structure creating natural air currents that regulate the temperature, much like those ancient Persian wind catchers. We see this same principle in the fluid, bone-like supports of bridges and the surfaces of buildings designed to shed water like a lotus leaf. This is not a new idea. It is a high-tech return to our oldest teacher, the Earth itself. Our search for truly sustainable, circular construction is also leading us back to ancient practices. The modern ideal of a circular economy, where waste is designed out and materials are endlessly reused, finds a direct ancestor in traditions of adaptive reuse that are thousands of years old. The Romans were masters of this, frequently repurposing the stone and columns from older temples and monuments into new basilicas and walls. In countless cultures, when a building fell into disuse, its materials were not sent to a landfill. They were carefully salvaged to become the foundation of a new home, a new wall, a new beginning. Today, we are relearning this logic with sophisticated recycling of steel and concrete, and with a renewed emphasis on using local, natural materials like rammed earth and bamboo, which have a minimal ecological footprint and have been used for millennia. As we develop technologies that would seem like pure magic to a Neolithic stone setter or a Roman engineer, we must pause and listen to the quiet, persistent questions they left for us in their enduring work. How do we create a shelter that truly protects, not just from the rain and wind, but from alienation and despair? How do we build in a way that inspires awe and connects us to our community and our planet? A three-dimensional printed house on Earth and a pressurized dome on the Moon are both answers to the same fundamental human need for sanctuary. The silent dialogue ensures that our breathtaking technological progress remains anchored to these timeless human needs and to the essential ecological wisdom that the first builders understood not as a concept, but as a condition of survival. Our journey from those first stone circles to the glittering towers of today is not a story of separation, but of profound connection. It reveals an unbroken chain of human ingenuity, where every generation truly does stand on the architectural achievements of its predecessors. This silent dialogue we have traced is not confined to a single discipline. It resonates through the very materials we choose, the mathematical truths we apply, and the ways we respond to our environment. It is present in the complex social organization required to raise a monument and in the spiritual aspirations we build into our most sacred spaces. Our tools have transformed from stone hammers to robotic printers, yet the essential challenges remain strikingly familiar. How do we create a structure that is meaningful, that endures, and that speaks to the human spirit? This enduring continuity offers us both humility and a deep well of inspiration. It reminds us that we are not the first to face these questions, and we will not be the last. We are active participants in a conversation that spans thousands of years, each of us adding a new chapter to architecture's grand, ongoing story. As we confront the urgent new challenges of sustainability, resilience, and building true community, we find that the wisdom embedded in ancient stones may be just as critical as our newest computational models. The silent dialogue between the builders of the past and the architects of the future is far from over. We are all part of it, and the next sentence is ours to